So under the introduction, by the 1960s, abundant evidence supporting the hypothesis of continental drift and seafloor spreading led to the formation of a more all-encompassing theory. This theory, called the plate tectonic theory, not only describes continental movement, but also proposes a possible explanation for how and why continents move. Most scientists subscribe to the idea that the movement of lithospheric plates is due to the movement of heated fluid material below these plates. Our driving question: what is the force that drives the plates? Self-assessment. The following statements relate to the driving question. Indicate if you think the following statements are true or false. Also specify how confident you feel about your answer by selecting H for high confidence, M for moderate confidence, or L for low confidence. Circle your choices for each one of these questions. Density is a measure of how much mass there is in a volume of a substance. Is that true or false? Identify your level of confidence. Pressure decreases from Earth's surface towards the center of Earth. Is that true or false? And then identify your level of confidence. Convection is the transfer of energy by the flow of a heated substance. Is that true or false? And then your degree of confidence. Everyone should be wrapped up with those questions. The following simulation is designed to illustrate the most widely accepted mechanism behind the driving forces necessary to move the Earth's lithospheric plates. After successfully completing this activity, we should be able to 1. Explain and describe the movement of a fluid within a convection current. 2. Define density and explain how differences in temperatures affect densities. 3. Explain how the Earth's asthenosphere plays an important role in plate tectonics. 4. Describe collision or convergent boundaries and give an example. 5. Describe spreading or divergent plate boundaries and give an example. And then finally 6. Describe sliding plate boundaries, also known as transform boundaries, and give an example. Let's flip to page number 58. What I would like you to do right now is answer the discussion questions number 1 and number 2. We will talk about these two questions. The first one is, what is meant by the density of a substance? And then the second one, what is convection? So try those on your own to begin with. Here in about 2 minutes, we will talk about those two questions. All right, so question number 1. What is meant by the density of a substance? This should be a little bit of review from things that we've talked about in the past. Density of a substance.
The weight of a substance that's in an object.
The weight of a substance that's in an object. Does anybody disagree with that statement? And if so, what corrections might you make to it? Nobody disagrees? Everyone's going to just go with it? Mass in a given volume. Does that sound a little bit more appropriate? Yep. Mass in a given volume. So what is the equation that we use to find volume? Think back to our density lab. What is the equation that we used for finding the density of an object? Nope. Not weight times height.
You put it in a cylinder or a liquid thing and like see how much the water rises.
Okay, so when we are looking at the amount the water rises, what are we measuring there? We're looking at how much that water rises. What are we measuring?
The volume.
Okay, we're measuring the volume. Another way to measure volume is length times width times height, right? So volume is one thing we're looking for, right? Volume is one thing that we're looking for. What else did we do with those little blocks before we put them inside of the water? Or maybe it was after we put it in the water to measure volume. We had to do one other thing prior to actually performing our density lab, or actually measuring the density of those materials. We weighed them. All right, so when we're weighing an object on a scale, what are we actually measuring? Measuring what? I heard somebody say it. Mass. We're measuring mass. All right, so density equals what over what?
Volume over mass.
Got it backwards.
Mass over volume.
Mass over volume. Density equals mass over volume. But explain to me, what exactly does that tell me? What does it mean? Because we're measuring something, and we want to understand it, not necessarily just that, oh, density is mass over volume, and that doesn't really mean anything to me. It's some equation that I'm never going to use again. Density equals mass over volume. What does that mean? Thinking about the atoms. What's going on with the atoms? Okay, yes? What about those atoms? When I've got two different materials, so for example, I got a piece of wood, all right, and we know that usually wood almost always has a density that is less than water, therefore it floats on water, right? Whereas if I had a chunk of metal that was the same size and I put it in water, it wasn't going to float. So why is that? Why would one of them sink and the other one not? What's happening at an atomic level with the atoms to cause one to sink and one to float? Viscosity plays into a little bit of why they float, but not quite so much. Density is a bigger part of this. So if we're talking about density, why would this guy float but a block of metal the same size, why would it sink? Thinking about the atoms.
Does the density of the object be heavier?
Okay, maybe. That's true. An object that is more dense but the same size would probably be heavier.
That the wood has less atoms than the metal.
Ah, good. The wood has fewer atoms than the metal. The wood's atoms are spread out farther in the same space. The metal's atoms are much closer together, therefore causing them to be more dense, or that metal to be more dense. And if it's more dense than water, it's going to sink. If it's less dense than water, then it'll rise. Everyone agree with that statement? Mm-hmm. Okay. So density is a measure of how closely packed atoms are in a substance. All right, next one. What is convection? What is convection? What is convection? Leslie. Okay, flow, does it have to only be air? Because we're using a simulation up here, and we aren't going to use air. So she says, the movement of matter, usually because there's energy that's supplied to that matter, due to density differences. Does it have to be a gas? So we know the atmosphere circulates matter, but does it always have to be a gas?
No.
What else could it be?
Water.
Could be water. What are those two things?
Substances.
They're both substances.
Atoms.
They both have atoms that make them up. One is a liquid and one is a gas. But what do we call those things together? They are both a substance that flows. What do we call a substance that flows?
Currentable.
Fluid.
A what?
Fluid.
A fluid. Substance that flows is a fluid.
But air's not fluid. I thought
It
fluid,
is.
I thought fluid
Gases
was
are
stuff that you
fluids.
consume like or you can consume like liquid.
It doesn't only have to be a liquid. A fluid is just simply a substance that flows. Gases can flow, liquids can flow. Okay? All right. Next one. This one's kind of easy. Fill in the blanks with the terms that complete the statement. At great conditions may cause solid rock to partially melt and flow. Extreme what and what inside the earth? Miss Santana, what is one thing that is extreme inside of our planet? What's that? I couldn't hear you. I'm getting old. My ears don't work as good. Okay, lava is pretty extreme. What does lava have that is extreme? And it's not lava inside the earth, it's actually called magma. But what is it that's extreme about it?
Hot.
It's hot. So there is extreme heat inside of our planet. What else is extremely great inside of our planet? Ms. Megan, what else is extreme about the inside of our planet besides just its heat? This causes heat inside of our planet. What would you have a lot of if I was to throw you in a hole and start burying you with a whole bunch of sediment? Pressure. Heat and pressure. Extreme heat and pressure are within the earth.
Well,
Number 4.
actually, she'd have that.
Yeah.
Mr. Windsor?
That was good analogy.
It wasn't a very good one, right? That was the best I could come up with. Number 4. Where is the Earth's asthenosphere, and how does it play an important role in plate tectonics? Where is the asthenosphere, and how does it play an important role
It's
in
under
plate
the
tectonics?
lithosphere and it moves the plates around because it's a flat enough surface and that they can shift.
Okay, very good. The asthenosphere is below the lithosphere. Remember, the lithosphere is what's thought to be broken up into the plates. The asthenosphere is thought to be a fluid-like plastic where it kind of moves around real slowly. So it works kind of like a conveyor belt.
What is it?
Asthenosphere is below the lithosphere, and it works like a conveyor belt moving the lithosphere.
Warm water.
This is just room temperature water. Yes, sir.
Okay, when you fill a cup with cold water, it's clear, but then when you let the water sit for a bit on hot water and then you fill the cup, it's all cloudy. Why is that?
I have no idea. It might have something to do with small air bubbles that are found in it.
Could be
Could be a lot of
salt
other
in
things.
your water too.
Could be the material that's coming out of just your water heater. Sometimes your water heater gets a lot of material build up inside of it as more and more material is heated in it.
Isn't the last one to show?
No, my screen's not working real great. It just,
But the camera
it
is
just
working?
Thinks it's working. It's just thinking.
Okay.
All right.
Think faster.
So we're going to look at 5, 6, and 7 real quickly, and then we're going to get into our lab. So number 5, what is meant by a divergent plate boundary, and can you give an example of one? What is a divergent boundary, Haley? Excellent. two tectonic plates that are moving away from one another. Divergent boundary is a plate where two plates are moving in opposite directions. Can anybody give me an example of where that may be occurring? Ashley? Nope, that's a different type of plate boundary. Good guess, though. Not the one by California. We're going to get to that one in a minute, though, so hold on to that one. Mr. Kevin, can you think of an area where two plates maybe are pulling apart from one another? I'll give you a hint. If two plates are pulling apart from one another, it's creating a pretty big valley. And certain things fill in valleys. We have a certain liquid on water that likes to fill in valleys. Where do you think we would have a divergent boundary where there's a valley filling with a liquid? There's a number of major ones on our planet. Together we call it a global one. You might choose to go fishing there. Where would you go fishing?
Wherever there's water.
Wherever there's water. All right, where is the vast majority of the water found on our planet? In the oceans. All right. So a place where there would be a divergent boundary is a place where two plates are pulling apart, therefore creating a very large valley. That valley is going to fill with water. So where specifically might we see a divergent boundary, Trey? In the ocean. Specifically what ocean, though? Andy?
Atlantic.
The Atlantic Ocean. The Atlantic Ocean is one we've talked about. In the Atlantic Ocean, there is a very large rift valley where two plates are pulling apart, filling in with water, creating the Atlantic Ocean. Yes, ma'am?
Was the Grand Canyon
No, the Grand Canyon is actually an area where erosion is occurring, where water's running off and it's basically just eroding all the sediment and moving it to a new location. Good question, though. Let's continue on. Number 6. What is meant by convergent plate boundary? And give an example if you can. A convergent boundary. Ms. Barrett.
Plates colliding?
Plates colliding, so two plates running into each other, coming right directly at each other. Can you give me an example in the United States of a convergent boundary? In the United States, where a convergent boundary is. Miss Brittany, can you give me an example? A place where two plates are colliding together. Alright, typically when two plates collide together, they push up on each other. So they create big rock mountains, right? Where might we have that in the United States? The Rocky Mountains, very good. Rocky Mountains are a location where two plates are pushing together, creating rocks to go up, creating mountains.
Miss Beatlesco needs Marty and Megan in the office.
Marty and Ms. Megan, you are needed.
That can be an office. Never be nervous when you go to the office because that could be a good thing.
I know,
They could
right?
be giving you some award. I mean, you never
Yeah,
know.
but she didn't sound like an award-winning.
All right, let's continue on. Number 7. What is meant by a sliding plate boundary? A transform fault. Give an example if you have one. What is meant by a transform fault or a sliding boundary? What's happening, Sam?
Two plates are slipping past one another.
Excellent. Two plates are sliding past one another. Are they sliding past one another like this?
No, they're going like this.
No, they're going horizontal. Good. So they're sliding past each other side by side. Can anybody give me an example? I haven't picked on you, Quincy.
Out there in California, right, on like Las Vegas, Los Angeles, and San Francisco.
Yeah, very good.
San Andreas Fault.
San Andreas Fault is between San Francisco and Los Angeles. That fault is where two plates are sliding past each other, and we see earthquakes very often there.
Is there like
Yeah.
What did you say, the San?
San Andreas.
So earthquakes would be another one too.
Is there like a gap between it?
Is there an actual like rift where you can see right down between them? Not really. There might be certain areas where you can kind of see that there's a little bit of a crack at the surface, but you really don't see where the two plates have big openings.
So would an earthquake be one too?
Any place that there are earthquakes, there can be a transform fault, but not necessarily always, because we can have, at divergent plate boundaries, we can actually have earthquakes. At convergent boundaries, there can be earthquakes.
Okay.
Yes, sir?
Is that why in that video that went up on the newsrooms and stuff where an earthquake happened?
Mhm.
Because they're in that area.
Yes, that is absolutely correct. All right, let's continue on to the next page. It says, make a labeled diagram of the density flow model setup on the illustration provided. Below, the 250 milliliter bottle is the hot bottle. So I filled this up with hot tap water, so as hot as I could get. So it's not super hot. It's not like you touch it and you're going to burn yourself. I added some red food coloring to it. The other two, right here and here, these both have cold water in them. We're going to cut it close here, aren't we?
Yeah, we're gonna overflow.
So we gotta put in the other one.
Where's your
too.
paper towel?
Oh, I got paper towel. We're good. I'll just have to take a cup out or so.
I can see like the little like density thing over top.
Disgusting.
Mr. John, would you go grab me a beaker off of the back sink and bring it out here so I can get some of the water out of here? Yes, sir.
If you go eye level with this cage, you can see the water over the top where it's
The
not.
buoyancy.
Why can you see that? Why can you see where it's bounding over top? Water has what property?
Learn this in like third grade, so we
Viscosity.
drop like pennies into this little cup to see how high we can get.
Why does...
Buoyancy, isn't it?
No.
Viscosity.
Surface.
Surface
We
tension.
don't want that one.
Surface
Surface tension.
tension.
Good. I want one of them that are bigger. Wide tops.
The round ones.
That's an Erlenmeyer flask.
Oh, what? I don't know.
It's just like something about your hands.
All right. So, hypothesis number one. Submerged in the center of the tank, and bottles of ice water are placed in the tank approximately 30 centimeters on each side of the 250 milliliter bottle. Describe the changes you believe will occur. And remember, we always write our hypothesis in the form of a if-then statement. If we put the red bottle, the red hot bottle inside of the water, right in the center here, then what do you think will happen? Thank you, John.
He couldn't find them, so we brushed two small ones.
John, you want the job done right? Don't ask the job.
Aren't they?
If you want something done right, I guess you just...
And get a girl to do it.
Yeah, I guess so.
Maybe actually
One side. Or like it's not lowering, it seems like on the other side.
Because the water's too far apart, then it won't break up on the other one.
So it's like, because the bottle acting like a
Yes.
dam, it won't let the water pass.
Probably because that's blocked.
All right, I think we're good now.
You gotta look at the bottle if you want the other side to go down.
It's getting there, slowly but surely. All right. With the red colored pencil, draw illustrations below to represent your mental picture of how the fluids will appear at 1 minute and then 3 minutes after the 250 milliliter bottle is submerged. Label the fluids. Hot red and cold will be clear. Go ahead and take a moment on that diagram and color them representing what you think will happen after 1 minute and after 3 minutes. What will happen after 1 minute and after 3 minutes?
So we're supposed to color the second diagram?
Yep, the first diagram and the second one. So the first one is after 1 minute, the second one is after 3 minutes. What do you think will happen after 1 minute? What do you think will happen after 3 minutes?
It's not the best drawing, so I won't let the drawing.
Okay, so Are there holes in those bottles?
There are no holes in the blue bottles. They just have cold water in them. That's your hypothesis. I can't dictate your hypothesis. What do you think will happen after 1 minute, and what will happen after 3 minutes? Go ahead and color it. Alright, looks like most of you are wrapping that up. Alright, this is the time where you need to find a place where you can see. You may want to fill in the center of the classroom. Those of you in front, sit down on the floor. Those of you towards the back, like Trey right now, your head is right directly in the way of others. They would not be able to see past you, so you might want to sit Indian style on the floor. They are cold, nice bottles. There's no water coming in and out, but they have cold water with like.
I think it's gonna shoot them like.
No, you need to have each other.
All right, let's get ready to observe. Make sure that everyone can see. If you're still coloring, go ahead and stand up so you can observe this. You can finish coloring in just a minute. This is just hot water with red food coloring in it.
Why is there a washer in there?
To give it a little weight so it'll sink to the bottom. All right, here we go. I'm going to take the top off after I get it in.
Oh, okay. Your hands look tiny inside.
Do they?
Yeah, they look puny.
It's leaking, okay?
That's all right.
Because he put his hands in there.
It's still gonna sink.
Okay, observe.
Looks like blood.
You know, a little shark that swims in there, just like eats it all up.
Why is it not? Well, mine's wrong.
I thought you were only gonna send it out of the straw, so I drew it out of the straw.
Me too.
Yeah.
Well, the cold water's going in the straw, so
you get to see what it looks like if you do a dead body. That's what you do. Mr.
I got it wrong.
Yeah, I screwed up.
You know what also happens with blood if you go swimming or something, you're bleeding, that it rises to
He hasn't gotten it able to work for a few hours.
And then those
so.
bottles are gonna cool it, and they're gonna go down, and they're gonna make like a convection current. Oh my goodness.
Mr. Windsor.
Whatever. Potato, potato.
No, I'm hungry. I want the little kid
They play with the minds of sharks to make them bigger, stronger, and make them so sharp. Big. You should watch it. And it has profanity.
It was too cold. I was like,
You guys can play in band later.
I'm not in band.
we'll enjoy
You guys seen that movie in the past, Mr. Trey? All
That's a
right.
good movie.
On the next page, page number 60. Observation number 1. Describe what happened. Was your hypothesis correct? Remember, we don't change the hypothesis. We just simply state whether we accept or reject our hypothesis. So if you reject your hypothesis, say you reject it. If you accept it, say you accept it. When you finish with describing what happened and your hypothesis, stating whether it's accepted or rejected, place inside the 250 milliliter bottle. Remember,
Well, I guess, yeah,
It's convection occurring in the bottle.
it's gonna rise.
I already have it done.
Okay, good. All right, I will agree with that.
What?
So where they are
Well,
meeting.
it's
is
coming
gonna
up
rise
because
and
I go this trail thing is bigger. That's exactly what I put. But yes, because yes, the warm water is going.
Also, take a moment here and observe what you see going on up inside the tank. What is happening with this red water to cause it to all of a sudden now be down on the bottom? Why is it down there?
Convection. It's getting cooler, so therefore, or it was getting closer to the sides, and it's getting cooler, so it's going down.
Excellent. So it sinks down because it becomes more dense and it's across the bottom. Before we take off today, your ticket out the door. What do you think would happen if we were to put 2 blocks of wood in the water directly above the hot water bottle? So right here, we got 2 blocks. The door, write it on a scrap sheet of paper if you would like. If you want to just verbally tell me on the way out the door, I will accept that as well.
Sounds good. Okay, it would separate